Homework 16, again, is the translating thing just like we did before with an exponential function. Here we have a logarithmic function. If x minus 1 equals 0, then x is going to equal 1, so it's going to move to the right 1. And then we have the minus 4 on the end, so it's going to move down 4. So we're going to grab it, move it to the right 1, and 1, 2, 3, 4 down. And we have our graph drawn over here. So same rules, what they're trying to get across. It doesn't matter if it's an absolute value, a quadratic expression, a cubic function, a logarithmic function, an exponential function. The translating is all the same. We go ahead and look at the next one. So if we look at this one, if x plus 2 equals 0, x is going to equal negative 2, so we move to the left, and then there's a plus 3, so we go up. So we're going to go to the left, 1, 2, and up, 1, 2, 3, and our new point's going to be right there. And if I could draw straight, my graph would look something sort of like that. One more of those. So if I look at this one, if x minus 3 equals 0, we're going to plus our 3, so we're going to go to the right 3 and then up 2. So grabbing my point, 1, 2, 3 to the right and 1, 2 up, we'd be at 4, 2. And so again, my graph will just automatically move over there and will look something sort of like that. All right, 4, 5, and 6, the basic properties of logarithms. Keep in mind that logarithms are inverses of exponential functions, so their rules are also inverses. If I think about an exponential function, if I'm doing x to the m times x to the n, I get x to the m plus n. So with an exponential function, when I'm multiplying with the same base, I add the exponents. With a logarithmic function, if I'm adding my logarithms, I'm going to multiply the numbers. So common base, base 4, that must be the same. So the log base 4 of 3, the log base 4 of 7 would combine into the log base 4 of 3 times 7, so 21. If I think about my rules for exponents when I'm dividing, if I have x to the m divided by x to the n, it becomes x to the m minus n. So with a logarithm, if it's a negative, it ends up going to the bottom of the fraction. The log base 5 of 8 minus the log base 5 of something equals the log base 5 of 8/9. Well, the number on the bottom of the fraction is a 9. So the log base 5 of 8 minus the log base 5 of 9 equals the log base 5 of 8/9. When I subtract logarithms, I change it to a division. And on my powers, if I have x to the m raised to the n power, I get x to the m times n. What that's telling me with a logarithm is if I'm multiplying something times my logarithm, it can then become the exponent. So this would be log base 8 of 5 to the second power. That exponent can be multiplied by the logarithm, or if I multiply it, it becomes the exponent. Of course, I would want to simplify that. 5 squared is 25. So number 5, if I look at that one, I have log base 3 of 7 minus the log base 3 of 5. It's going to be the log base 3 of 7 over 5 then. Because I'm subtracting, I end up dividing by that 5. Log base 7 of what? Plus the log base 7 of 4 would be the log base 7 of 12. Well, I have to say what times 4 gives me 12? Oh, that must be a 3. And then this one, I'm saying, okay, the 81 has to equal, and this would become the exponent here, so 3 to what power? 81 equals 3 to what power? So I'd say, okay, 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 81. I'd have fourth, so this would have to be the fourth power, right? That exponent would go out in front, so 3 to the fourth power is equal to 81. And we're going to use this bottom rule a lot when we are doing logarithmic equations, where if we have an exponent, we move it out in front and multiply it by the logarithm in order to simplify and get our variable out of the exponent. One more of those. So on number 6, log base 7 of 2 plus log base 7 of 9. I'm adding my logarithm, so I multiply log base 7 of 18. Part B, log base 5 of what? Minus the log base 5 of 7 would equal log base 5 of 6/7. The first box would have had to be a 6. And then log base 8 of 25 equals 2 log base 8 of what? I'd say 25 is equal to what to the second power then, right? This becomes this exponent. Well, 5 to the second power is 25, so that number would have to be a 5. So those are your basic rules for logarithms. If we're adding logarithms, we combine it into one expression by multiplying, subtracting logarithms by dividing, and that we can multiply a number times the logarithm. It would then become the exponent of our number. The next ones, we are going to compute things like the log base 8 of 6. We've already done some where we could actually do the calculation. When we had log base 2 of 16, we said, okay, 2 to what power equals 16? And we knew 2 to the fourth was 16, so x had to equal 4. Well, on these ones, if I tried to rearrange it, I would say 8 to what power equals 6? Well, it's going to come out to a really weird number, so we have to find a different way of solving it because we can't do it that way. So we have a formula. Our formula says this. If I have the log base b of a, I am going to take the log of a divided by the log of b. And those could be anything that have a common base, but what we're going to do is base 10 because our calculator can do base 10 numbers. And so we're going to use our calculator and do the log of 6 divided by the log of 8. Before we do this one, let's do it with this one that we knew what the answer was. If I use my formula, I'm going to take the log of 16, that outside number, divided by the log of the base, which is base 2. So I'm going to grab my calculator, find my logarithm button on the Casio. It's right here in that second column, the third one down. So I'm going to punch in log of 16 divided by log of 2. Now again, on the Casio, you don't need parentheses. On Texas Instrument ones, it would put the parentheses there. The only time you need the parentheses is like if you have a fraction or some math problem in there. So in this case, if you hit equals, you should get the 4, which is what we already knew the answer was on that one. Here then, if I do the log of 6 divided by the log of 8, I get 0.86165. Round to 3 decimal places, so 1, 2, 3. That means there's a 6 behind there. I have to round that up. So 0.862 is what I'm going to get for the value of x. So when it says to round to 3 decimal places, it means 3 places after the decimal. In other words, a thousandth spot. So if I'm going to compute the log base 8 of 9, I'm going to take the log of the 9 divided by the log of the 8. So log of 9 divided by log of 8. I get 1.0566, so 3 decimal places means I'm going to use 1.057. Again, I've got to round that one up. And then number 9, I'm going to do the log base 1/6 of 9. So I'm going to do the log of 9 divided by the log of 1/6. And on our calculator, we've got to put that 1/6 in parentheses. You can just use the division key instead of the fraction key, which is what I've been doing all along anyway. So the log of 9 divided by the log, parentheses, 1 divided by 6, or 1 fraction 6. And so I end up with negative 1.2262, so to 3 decimal places, negative 1.226. So not so bad, like I said, those previous ones that we already calculated by writing them as exponential functions, we could have done using our calculator, but they wanted you to practice rearranging it into exponential form. Now we do the ones where you can't, and you have to use your calculator to evaluate them. The log of the outside number divided by the log of the base. 10, 11, and 12, we are now going to solve some exponential equations by finding a common base. What we want to do, first of all, is try to rewrite these with the exact same base. Sometimes you only have to change one, sometimes you have to change both of your bases. But in this case, I can rewrite 64 as 2 to a power. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, 32 times 2 is 64, so I need 2 to the 6th power. And I wrote my 2 down. 2 to the 6th power. So I have 2 to the 5x minus 3 equals 2 to the 6th raised to the 3 minus 9x. When I raise to a power, I multiply. So 2 to the 5x minus 3 would equal 2 to the 18 minus 54x. Now that my bases are the same, I could basically ignore them that they're there. If my bases are the same, my exponents also have to be the same in order for them to be equal. So 5x minus 3 would have to equal 18 minus 54x. And then I just go ahead and solve that like I solve the rest of my equations. I'm going to add my 54x and add my 3. So 59x would equal 21. I'm going to go ahead and divide by 59. So x equals 21/59. Not a real pretty answer, but one that works. So number 11 is the same kind of thing. I've got base 10. I really can't write 10 to a different base, but I can write 100 as 10 to the 2nd power. So 10 to the negative 6x is going to equal 10 squared to the 2 minus 2x. So again, I have to go ahead and multiply that out. So I would have 10 to the 4 minus 4x. Now that my bases are the same, my exponents could be set equal to each other. Negative 6x would equal 4 minus 4x. So solving that, I'll go ahead and add my 4x to move it over. Negative 2x would equal 4 when I divide. X is going to equal negative 2. 4 divided by negative 2 is negative 2. And one more of those. So number 12, I have 64 equals 32 to the negative x minus 3. Now here, I can't write 64 as 32 to some power because 32 to the 1st is 32 and 32 to the 2nd is way bigger than 64. But I can write these both as base 2 numbers. 64 again was 2 to the 6th, so we did that earlier. 32 would be 2 to the 5th. So I'd have 2 to the 5th raised to the negative x minus 3. So 2 to the 6th would have to equal 2 to the negative 5x minus 15 then. Now that my bases are the same, my exponents have to equal each other. So 6 equals negative 5x minus 15. I'd add my 15. 21 equals negative 5x, and go ahead and divide. Negative 21/5 is my answer for x then. (13, 14, 15), continuing on with finding a common base. This time our exponents have quadratic expressions in them also. So really doing the same thing, trying to rewrite them with a common base if we possibly can. So 27 is 3 to the 3rd. So I'd have 3 to the 3rd raised to the 3x minus 3 equals 3 to the x squared plus 2x minus 27. Multiplying that out, I'd have 3 to the 9x minus 9 equals 3 to the x squared plus 2x minus 27. So now that my bases are the same, I can set my exponents equal to each other. 9x minus 9 equals x squared plus 2x minus 27. Since I have a quadratic expression, I've got to move everything over and set it equal to 0. So minus my 9x and add my 9. X squared minus 7x minus 18 then is what I get there. So solving that by factoring, x and x, a plus and a minus. I'd have to have a minus 9 and a plus 2 to get minus 7 in the middle. If x plus 2 equals 0, then x equals negative 2. If x minus 9 equals 0, then I have a positive 9 when I move it over. And so I get two solutions, negative 2 and 9. So number 14, same kind of thing. I can rewrite 16 as 2 to the 4th power. So 2 to the x squared minus 16x plus 24 is going to equal 2 to the 4th raised to the 9 minus 3x. So 2 to the x squared minus 16x plus 24 is going to equal 2 to the 36 minus 12x. Multiplying out my exponent. Now that my bases are the same, my exponents have to be equal. So x squared minus 16x plus 24 has to equal 36 minus 12x. Again, we have a quadratic expression, so we have to set it equal to 0. I'm going to add my 12x and subtract my 36 then. So x squared minus 4x minus 12 is equal to 0. And factoring. X and x, a plus and a minus, and I'd have to have a minus 6 and a plus 2 to add up to minus 4. So if x plus 2 equals 0, I'm going to write it over here. I get a negative 2 answer. If x minus 6 equals 0, I got to add my 6, so I get a positive 6 answer. So I get x equals negative 2 or positive 6. And one more of those. So on number 15, for my little box to disappear, I have 25, which I can write as 5 to the 2nd power. So 5 to the x squared minus 24x plus 22 equals 5 squared raised to the 3 minus 8x. So 5 to the x squared minus 24x plus 22 is going to equal 5 to the 6 minus 16x. So our bases are the same, our exponents have to equal each other, so x squared minus 24x plus 22 equals 6 minus 16x. Setting that equal to 0, I'm going to add my 16x, I'm going to minus my 6. So I get x squared, let's see, that would be minus 8x, and 22 minus 6 would be 16, plus 16 equals 0. Factoring x and x, since the end is positive, they're both same as the middle, a minus and a minus. Factors of 16 that add up to 8, 4, and 4. I have a double root, so that means I'm only going to have one answer. If x minus 4 equals 0, then x is going to equal positive 4, and that's going to be my solution. (16, 17, and 18), I can no longer rewrite these with the same base. I can write 16 as 2 to the 4th, but 17, the only way I can do it is do 17 to the 1st power. So what I have to do is I can either take the log or the natural log of both sides. Since in the directions it tells us to use base 10 logarithms, I'm going to take the log of both sides. But technically, you can also do the natural log of both sides. So what I'm going to do is I'm going to have the log of 17 to the negative x minus 3 equals the log of 16 to the negative 8x. Now that they're written as logarithms, I can take the exponent and multiply it by my logarithm using those basic rules for logarithms. So negative x minus 3 times the log of 17 is equal to negative 8x times the log of 16. Now here, I want to solve this for x, and since there's an x on both sides, I'm going to have to use my distributive property. Otherwise, I'd probably just go ahead and divide by my logarithm, but I can't divide by my logarithm in this case because I've got x's already on both sides. So I'm going to use my distributive property. Negative x log of 17 minus 3 log of 17 equals negative 8x log of 16. Since I want to solve this for x, I want my terms with my x's on one side, anything without an x on the other side. So negative x log of 17 plus 8x log of 16 is going to equal negative 3 log, nope, not negative, positive 3, because I moved it over, positive 3 log of 17. So I had to add that when I moved it over. I also had to add that when I move it over. So what I can do here, since I've got x's in both my terms, is to factor just the x out of there. X times negative log of 17 plus 8 log of 16 equals 3 log of 17. Notice I took just the x out of both of those. To solve this for x, then, I can divide by this stuff here. So x is going to equal the 3 log of 17 over all the stuff here in the parentheses. Negative log of 17 plus 8 log of 16. And they don't want us to evaluate it, they just want you to use an exact answer. Otherwise, we'd have to use our calculator to evaluate approximately what that would be equal to. Number 17, again, we have a base 7 and a base 9. No way you're going to get those written with the same base, so we're going to take the log of both sides. The log of 7 to the negative x minus 7 equals the log of 9 to the negative 6x. Now that they're written as logarithms, we can multiply our logarithm by our exponent. So negative x minus 7 times the log of 7 equals negative 6x times the log of 9. Using our distributive property, negative x log of 7 minus 7 log of 7 equals negative 6x log of 9. I want to move my x over here, anything without an x over there. So negative x log of 7 plus 6x log of 9 equals a positive 7 log of 7. Going to factor my x out. So x times negative log of 7 plus 6 log of 9 equals 7 log of 7. I can then go ahead and divide. So x is going to equal 7 log of 7 divided by all of the stuff here, negative log of 7 plus 6 log of 9. And one last one on here. Again, we have bases that can't be written the same, so we're going to do the log of both sides. So I'm going to do the log of 13 to the negative 6x equals the log of 3 to the x plus 5. So bringing my exponents out in front, negative 6x log of 13 equals x plus 5 times the log of 3. Using my distributive property, negative 6x log of 13 equals x log of 3 plus 5 log of 3. And since I don't like all those negatives, I'm going to move this one over here, so then I'm going to move anything without the x over here. So I'm going to have negative 5 log of 3 equals x log of 3 plus 6x log of 13. It'd be okay if you moved them the other way. Your signs will just end up being opposite of what I did. Factoring out my x. And then, of course, dividing. So, negative 5 log of 3 divided by the log of 3 plus 6 log of 13 is going to be equal to x. Now be careful when you type that in. That negative is up on top with the 5. Shouldn't matter if it's out in front, but just to be on the safe side, it's best if you hit the fraction button first, type that in. Now, that's all the logarithm stuff we're going to do. There is a lot more logarithm stuff that we could do, but just to give you the basics of logarithms, which you should have already done in college algebra, probably won't do a whole lot of logarithms in calculus, but still you kind of have to know those basic things.